Welcome to our mid-semester design presentation. We are Gait Analysis System, or GAS for short. These are two of our team members. I am Zoe Fowler. I am the team lead, and I am in charge of the ankle bracelet subsystem.
Hi, I'm Chris Slagle. I'm working on the hardware design, specifically the belt subsystem and subsystem connection.
Hi everyone, I am Omar Saeed. I'm responsible for software design, specifically smartphone application.
Hi, I'm Holiday Garrison. I'm responsible for software design, specifically sensor detection.
Hey y'all, I'm Ryan Hobson, and I'm responsible for software design, specifically data processing.
This is our faculty advisor, Dr. James E. Fowler. He is a current professor here at Mississippi State University in the Department of Electrical and Computer Engineering. He obtained his bachelor's, master's, and PhD from Ohio State University.
And this is our external advisor, Tracy Blackstock. She is a physical therapist who works in home health and outpatient therapy with Stay Home Health and Hospice, and she received her doctorate in physical therapy from A.T. Still University in Missouri.
So gait analysis is a way for physical therapists to analyze a person's walk. It's very important for correcting injuries that hinder a person's ability to walk correctly. So there are many pre-existing methods. However, they're either expensive or they just do not record any data. So oftentimes physical therapists assign their patients homework, such as walking sessions, to do in between their therapy sessions. However, there's no way to monitor these patients during these walking sessions, and so it's very difficult to actually gauge whether a patient is truly improving or not.
So our solution is GAS, which is used to analyze the patient's gait. It's made up of a belt and two ankle bracelets, which are connected via wires. There are sensors located on the belt and ankle bracelets to record all the important gait information from the patient. And then the physical therapist can connect to GAS via USB with no training whatsoever.
Now for our outline, we'll start with constraints, then go into our approach and finish with our progress and conclusion. Now for our constraints, we'll start with our technical constraints. It's really important that our battery life lasts at least an hour and we have enough memory storage to store an hour's worth of data, because that's the maximum walking session that will ever be prescribed, though they're usually closer to 15 to 30 minutes. For the waist and ankle belt sizes, we decided that the minimum lengths for the waist would be 91 to 111 centimeters, and for the ankle would be 19.7 to 24 centimeters. This comes from an article from the CDC listing those as the average. And for our measurement frequency, it needs to be at least 115 measurements per minute for each of our sensors. That's because each sensor needs to be able to take one measurement per step, and according to our external advisor, the average human cadence is about 110 to 115 steps per minute. For our measurement accuracy, it's plus or minus 5%, because that's within a range where when a physical therapist looks at that, they'll still be able to make something of it and see if the patient is actually improving.
There are practical constraints must be met. First, GAS should be lightweight with less than 2.3 kilogram to make it easier for the users to work with. Should be inexpensive with around $150. Should be safe and secure to avoid any trip hazard that cause injury and prevent the wires that could be tripped over. Finally, and most important one, in practical constraint, it should record all the data that's going to be used by physical therapists, such as the average width between the user feet, the average and time direction, the average time taken for each step, and the average time and direction for arm swinging.
And lastly, we have our engineering standards to make sure we can. But first is the universal serial bus. We're going to use a 2.0 connection, and that's just to make sure we're compatible with any USB 2.0 wires out there. And then ID 2079, that implies we need an instruction manual for make sure our device is usable by elderly people, and make sure things like the font is readable enough. Lastly, we have our IEC 6228. That makes sure that wires that we're going to include are they can conduct electricity, but small enough where it can be worn comfortably. And now we can move on to.
So now onto our hardware overview.
We can move, yeah.
So gas is composed of one belt and two ankle bracelets. So we see on the left leg, there are two PIR sensors. So we have one PIR sensor located on the outer ankle and one PIR sensor located on the inner ankle. The outer PIR sensor is there for nearby object detection, such as animals or people. And so when this sensor is high, all measurements taken during this time will be discarded. The inner PIR sensor is there to detect when the feet move into a parallel position. So on the opposite leg, we have, again, an outer PIR sensor for nearby object detection and an inner ultrasonic sensor. So when the inner PIR sensor on the opposite leg detects that the feet are in a parallel position, this sensor sends a signal to the ultrasonic sensor to take a distance measurement. So on the belt, we have two PIR sensors located on opposite ends nearest to the arms. These are there just to detect arm swinging movements. We also have an LED located on this belt, which serves as a visual indicator for when the device is on. So the microcontroller selected for gas must have at least 5 digital pins, 1 analog pin, and include both 5 volt and 3.3 volt regulators. So all the microcontrollers selected that we looked at met these 3 basic requirements. However, we selected the Arduino Uno Rev 3 as our microcontroller because it met all the requirements and it also had a lower cost than both the Mega and the Do. PIR sensors can detect the presence of an individual very easily due to their ability to detect infrared radiation. So this table just lists the various PIR sensors considered. So one of the most important things considered when selecting PIR sensors was the delay time for taking one measurement. So the inner PIR sensor on the leg's main goal is to detect when the legs are in a parallel position. So for this delay time, the maximum delay time is 0.6 seconds. So this is just because the average human cadence is around 110 to 115 steps per minute, which translates roughly to 0.6 seconds per step. So as we can see, the SEN 13968 meets this requirement, making its delay time 0.4 seconds for taking one measurement. And so because of this and the fact that it met all of the requirements, we select as our PIR sensor. Ultrasonic sensors are inexpensive and they're able to recognize objects easily at a very high accuracy rate. So because the ultrasonic sensor is informed by the PIR sensor when to take a distance measurement, the 0.4 seconds delay time for the PIR sensor informs the delay time needed for the ultrasonic sensor. However, all the ultrasonic sensors that we looked at met this requirement. So the HCSR04 was selected to be our ultrasonic sensor because it met all the requirements and it also was the least expensive.
This leads us to our subsystem connection. So as mentioned earlier, the subsystems are connected via wires, and this was selected over the wireless Bluetooth connection because 1, the wired connection is less expensive and it's more lightweight than the Bluetooth connection. 2, there's less current consumption overall, which results in a longer battery life. And 3, when everything's connected with wires, it's all one piece, which is harder to lose than the 3 separate pieces that would be created from the Bluetooth connection. The only con from the wired connection is the trip hazard, but this can be completely avoided with a knee brace. Wired, there's no wire for the over. Next is the memory chip section. So our big requirements here were that the memory chip needs a storage space of at least 55 kilobytes. It needs to fit within the supply voltage range of 3.3 volts or 5 volts, and it needs to be flash memory so that it is easily written to and read from. And out of all these choices, we selected the Arduino MKR Mem Shield. While it is the most expensive, it works really well with the Arduino Uno Rev 3 microcontroller board that we selected, and it is flash memory. Our final hardware component is the battery. While we needed the battery to be inexpensive and small and lightweight, the more important requirements were that the battery has an output voltage of 7 to 12 volts and a capacity of 134 milliamp hours. This capacity allows the battery to fill the technical design constraint of the device's battery life lasting at least an hour. The battery also doesn't need to be rechargeable, and it needs to be replaceable instead, so that whenever the device is out of power, the therapist or user can simply replace the battery instead of waiting an extended period of time for the battery to recharge. With all this in mind, we selected the 6LR61 battery, and this is just a typical 9-volt battery you can find in Walmart or buy online at Amazon, and it fits all these requirements, and its battery life makes the device last around 4.5 hours.
Now for the software overview. The software mostly consists of 5 main parts, that being the control detection, which is how the sensors are interacting with our Arduino, all of our data processing, our memory storage, our data transfer from the belt to the app, and our app itself. With the control detection, it begins with the power button being pressed to turn the belt on. If the memory is full or if the battery is low, then the LED will begin to blink. Otherwise, the sensors will begin initializing themselves, and then it'll check if the USB is plugged in. If the USB is plugged in, initialization will stop and it'll wait for the app to say that it's ready for data transfer, at which point it'll package and transfer the data. If the USB isn't plugged in, it'll continue the initialization of all of the sensors, and then when the sensors are done initializing, it'll begin measuring, saving, and processing all the data until the power button is pressed to turn it off.
So how are we going to get what we need from the sensors? This is where the data processing comes in. Let's first start off with the PRI. There's multiple implementations with reading the pin voltage high. The first one is incrementing the arm sway counter. When reading the appropriate leg is matched with the appropriate arm, which will increment the counter. It's going to raise a flag, or we're going to have a flag raised when it detects nearby objects to stop recording data so we can get that accuracy. And thirdly, it's going to trigger the ultrasonic sensors, which I will mention later when I talk about if the feet are parallel. I'm taking between arm swings and the ratio of position to arms relative to feet. That's very important. Secondly, the ultrasonic sensors. We're going to read in the distance and sound. And I mentioned earlier, we're going to talk about the parallel position of the feet. Well, there we're going to start a timer to calculate how long a user takes one step, and we can have a counter for the number of steps they take. And then to tag along with that, we're going to measure the width between the user's feet. So from that data set, we can calculate the length of one walking section, the average width of the user's feet, and the average time taken for each step. Those are very important for the physical therapist. And now for the memory storage section, we mentioned earlier that we're going to use the EEPROM and the flash memory to keep the data stored even if the device turns off for one session. It was mentioned also that it will be taken with one session will be about 55 kilobytes. And so that comes from the calculation that we're going to use unsigned integers to store all the counters I mentioned earlier in the last slide. And the data, like I said, will also be transferred to USB. And so the Arduino software has a communication for that. And also earlier we mentioned control detect notified if the memory is full with the LED.
Now time to transfer the data, which is the exciting part of the project. First, the user gonna need the USB cable to connect the smartphone application to the belt. Second, the user need to turn on the belt so the belt can recognize the USB cable and deactivate all sensors. Now to start packaging data to the application, the user need to click on the upload button and start packaging data. So to view all the data of that specific session that I just uploaded, the user just need to refresh the main page and display the data. Now let's go ahead and explain the smartphone application, how it's gonna be. First, we choose a smartphone application over desktop application because the availability of a smartphone application make it easier for physical therapists to upload data and view data at any point of time, which make them which give them the ability the option to allow their patients to view the data or upload the data by themselves at any point of time. So now this is the smartphone application. As you can see from the first image is where the user need to upload the data to the application. as now the user can view all the sessions listed on the application along with the information of that specific patient. Now in the next image is where the user now go ahead, if he needs to view that specific session, you need to click on that specific session, and all that charts, diagrams of that specific session is going to be displayed for the physical therapist, so the physical therapist can judge or analyze the situation of their patients. This data could be the average width between the user feet, the average time taken for each step, and the average time direction of arm swing to decide the status of their patient.
I'm just gonna jump in real quick, guys. You're at the 15-minute mark, so wrap it up.
For our progress, we've already submitted our proposal and our constraints, and we're getting our final details done on our approach document, and we've already put in our first parts order. By the end of October, we'd like to have a prototype working and most of the code finished so we can spend November testing and debugging.
In conclusion, we're making a home healthcare product that is easier to make, easier to use, and way cheaper than other today's solutions. With that being said, I want to open up the floor for any questions.
All right, thank y'all. I thought that was a great presentation. I enjoyed it. I'll of course submit this in the team evaluation forms that y'all will receive as well, but here's just some quick feedback from me. Let's see. Just a minor comment. You had the block diagram, but the little person in your block diagram didn't seem very happy. But that's just
Halloween diagram.
Halloween theme.
Halloween,
It's October.
Okay, I missed that. I'm like, I'm not sure why I can see its brains and stuff.
Yeah,
So
and its teeth and stuff. I noticed.
yes. Okay.
Right.
Are you planning? I think I mentioned it last time. Are y'all planning on doing graphs and charts? It sounds still like you're doing averages or tables for the smartphone app.
So,
Yes, Chris, would you like to?
oh yeah, no. So the idea is to represent like for the cadence, the average step time per minute for the patient, represent that as a moving average on a graph for the physical therapist, so they can see how that changes over time, and that maybe that specification can be made by the physical therapist, right? And then for like the number of steps during the walk and like the total time that the walk took, right? You know, that would be represented in like a table, or a chart or something like that.
Okay, that sounds good. I think that would be an important thing. Another just encouragement. I feel like at the beginning, I understand that gait analysis is important, but I'd love to see some concrete examples. Who would be benefiting from it, and what kind of how would this improve people's health? How would this help them avoid injury or help them recover from injury? Just really personalize it and let people see this is not just an academic problem, but it's really going to touch people, because I think this is so important.
Yes, sir. To add on to that, because of our time constraint of 15 minutes, we couldn't fit absolutely everything for this presentation. So we added this appendix right here for our target audience, right? And so this device is targeted towards physical therapists, but specifically physical therapists who work in outpatient therapy, home health, and inpatient rehabilitation. According to the CDC, most of that group is the elderly group on Medicare, ages 65 and older, right? And those people are sometimes known for fall risks, right? And this gait analysis device or GAS helps analyze those elderly patients' gait, determine whether or not they're a fall risk, and then the physical therapist can then take that information and use to help them become less of a fall risk. Is the general idea. However, there wasn't really enough time to kind of fit that into the presentation without, cutting some of the hardware components and software components.
Sure, but let me encourage you. I would actually cut hardware and software to get that in, because unless people believe it matters, they don't care about how you do it.
Yeah, sure.
Yeah,
Yes,
yeah, I would agree, and really, I mean, all the other design teams before you guys for the past several semesters have had the exact same time constraints, and they've managed to make it work. I think you guys can make it work. It'll just involve more practice with your time management, I think. This was a crafty solution, though, to using the appendix. Yeah, clever, but I agree with Dr. Jones. I think you should shave down your time other ways.
Hey, I thought there's a good couple comments or questions in the comments if y'all would respond to Jake and Brian.
Okay,
I cannot see the comments right now.
for Jake, he said why we don't use like the computer, the data, which is one of the options for us because the app eventually is going to be recorded on the cloud and just be accessed anywhere. That's what we plan eventually to do it. That's more features to make it accessible for physical therapists.
For the second question, Chris, can you go to the problem slide?
Yep. Here, let me.
Okay, so these two images represent what our competitors are. So the first image is the gait belt. The gait belt doesn't record any sort of gait-related data at all. All you do is you just put it on the person that can't move themselves, and then someone else moves them. That's how they move a person. So that's what I meant by like pre-existing methods are either expensive or do not record data. For image one, that is, you know, it doesn't record data. For the second one, this is the expensive option. So oftentimes you can tack on like expensive sensors all over a person's body and then use equipment to analyze. Like it's kind of like what is it? How do they do? Chris, you know what I'm talking about? How they do the
gait analysis, analyzing how a person walks, has usually been done by a computerized program in a room over the years. Like, for example, when my mother was back in grad school in the 90s, they would stick like lights on the person walking down a dark hall, and they would have a computer system taking pictures of the person every so often and seeing how the lights were changing as the person walks along. Computer systems nowadays that analyze gait aren't too much different from this, but the thing is they can't move and they're stationary and they're super expensive, right? So it's hard to have an inexpensive solution for something like that without, you know, putting in the form of a wearable device.
A lot of external setup versus our product is supposed to be designed to, you know, accommodate the user on the go, like in parks.
A quick comment. That is a great point. Next time, Chris, please invite her. I would like her feedback on this presentation. I think that would be fantastic to, again, have someone to sort of provide some professional evaluation. And unfortunately, I need to go to the next presentation. Again, very well done. I appreciate what y'all have done, and I will follow up and gather all the peer evaluation and advisor evaluation and pass that on to y'all.
Thanks so much, Dr. Jen.